Hello everyone, welcome to the course. Today the topic will be foundation models. And if you recall the logical structure of our course, this is the first time that we skip the view from an isolated AI within its life cycle and now look into AI within systems. So to shortly bring up this slide so that we recall it, we started with the original motivation and made sure that we understand our terms, and then went through this entire AI life cycle, right? From data gathering in the initiation step, over building our first models, evaluating them, deploying them in the field, and then hopefully dealing successfully with concept drift in the last one. Now, in the logic of the upcoming next 3 lectures, we will think of AI within a system. That means it's no longer an isolated entity somewhere in a potentially artificial context, but it's a real world entity embedded into existing systems and networks, typically where value is co-created, right? So we have many different AI entities or agents collaborating with each other, or larger teams consisting of humans and AI agents, things like that. And the fundamental step to understand why and how this works are foundation models. So let's dive into that right now. And I think there's a pretty neat article from The Economist saying AI could fortify big business, not append it. So this article suggests that AI could strengthen the dominance of large established companies, tech companies like Google, like Meta, like Apple, like IBM, which makes it more difficult for smaller innovative firms to compete because the power is now concentrated around these foundation models, these large AI models that we'll talk about today. On the other hand, you have things like the European Commission, and from the speech that you can see up here from February 2024, it's emphasized that they really want to prevent this monopolization by big tech firms, ensure that the benefits of AI are accessible across the market, across different sizes of companies. So I think that's a perfect motivation to start with the topic, because together these perspectives highlight the tension between innovation-driven consolidation on the one hand, and the other one, the need for open, equitable AI access. So that's also a topic that we'll discuss further when we come to AI ethics and fairness. But it serves as a good motivation, and that's why we should have a look at the question, what is a foundation model in the first place? Which we'll do in the introduction. Then we will talk about multimodality in data, why this is the case in many real-world applications and how foundation models handle those. We'll talk about generative foundation models. That's a typical case when people speak about foundation models nowadays. They talk about the generative aspects of these models, like large language models, for example. And then I want to give you a few insights from recent research and industry examples. So, what is the idea of a foundation model? So far, we've dealt with machine learning models in a particular way. We had a data set, and on top of this data set, we wanted to build a machine learning model which is able to predict one of the features, one of the targets in that data set. We did our training test split, built the model, and hopefully it would be very good at detecting the value, the predicted value for a specific task. And we would deploy it and so on. We've discussed all of that. Now, foundation models have a paradigm shift because they want to enable 2 things. First of all, transferring across different tasks. Again, so far the models that we built, they could be used for one task and one task only, right? For this very, very specific task under very, very specific assumptions also on how the data set looks like. So we want to transfer that. And second, we also want to scale that. So those are the 2 main characteristics that differentiate a foundation model from the previous models that we talked about. And there are typically 2 steps happening here. The first one is a pre-training that you can see right here. So that's training a model on a broad data set depicted by the various cars that you can see here on the slide. And this allows the model to learn general features and any pattern that is applicable across multiple scenarios, right? So it could detect the general shape, for example, of a car, of a vehicle, of a being. And the next step is then called fine-tuning. And this specializes the model for specific tasks, for typically smaller, more nuanced tasks and data set. For example, in this case over here, these could be different types of vehicles, such as the buses over here or the monster trucks. And hopefully this enables the model to make more accurate prediction in these specialized contexts that you can see over here, while still leveraging this foundational knowledge from the pre-training step that you can see here. And this demonstrates the idea of transferring the knowledge and scaling it up. Now, what are foundation models? What are their characteristics? The first is they're built on huge data sets, right? You can see the example over here from the diffusion database with 14 million image prompt pairs. So the data sets are nothing compared to anything that we did so far. They are really, really huge. And due to that size, we hope that this broad pre-training enables a very good generalized understanding, or you could even say potentially knowledge of a certain phenomena, like in this case, images, right? Like the shape of people, of cars, of flowers, and so on. So, first characteristic, they require huge data sets to train on. Second one is, we will leave now the realm where we have predetermined labels. Earlier, we always had the case that, for example, we wanted to predict whether a part was faulty or not. So we needed this label, part is faulty or is not faulty. Or in the case of medicine, MRI scan, we needed to have the radiologist to clearly label certain areas in certain pixels, telling the machine learning model where a tumor is, for example. Now, here we are now shifting towards something called self-supervised learning, which is a really interesting thing. To be honest, it's a sub-method of supervised learning, you could say. So if we have a sentence, and we can explain it with that really well, like the university has a beautiful campus. What happens here is that we have the history of these tokens, of this string of these words, and then a final most probable next token, or prefix, suffix, etc. And in this case, that is campus. What we implicitly have here is a label and an input. And if you recall the very fundamental definition of supervised learning, it's the matching of an input to an output, or to a target. And the same is happening right here. So for the self-supervised learning, we will just act like, in this case, for example, the last part of this token is the target without ever anyone explicitly labeling it like that. And then slowly over time, you could iterate through different tokens and exchange that target here, right? So the system is able to learn by itself without the explicit need of someone labeling the data, because it assumes that there's a pre-labeling existing. We just have to, cut out certain parts of this token, right, and act like this was the target. So the assumption is that all the knowledge that we require is already part of the data, and we can self-supervise this learning process. So no more human input is needed. Second characteristic of foundation models. Third one, the models are really, really large. We talked about the data before, but now it's about the very models. And you can see this graph over here, which shows how large these models have become, and they're getting larger and larger. And on the y-axis, you can see the amount of parameters in billion, and on the x-axis, you can see the timing. Now, one thing I need to make really clear here is that these are different parameters than the parameters that we talked about when it came to the model tuning. The parameters in the model tuning were characteristics of the algorithm that we could use to tune its behavior. When we talk about the size of models with parameters, we're talking about weights and biases that this model learned. So the parameters right here in these deep neural network based models, those parameters are adjusted during the training by the optimization algorithm, whatever you chose, for example, gradient descent, to minimize the error in the training data. So the parameters here give you a sense for how large the model is, how many weights and biases it has, right? So give you an idea on the resourcefulness of the training process, whereas parameters before in modeling and evaluation were all about fine-tuning the model to receive a better performance, right? So we can see foundation model, huge data sets, unlabeled data, and large models. But this wouldn't be a scientific talk if it didn't come to a definition, so let's have one. A foundation model is itself incomplete, but serves as the common basis from which many task-specific models are built via adaptation. So we have this pre-training where we build a generalized common basis, and then we have so-called downstream tasks where we then adapt the model for very task-specific models. Okay, now, what does that typically look like? For companies utilizing foundation models, two crucial steps are identifying the necessary adaptations that we need for the deployment at the very end of this process that you can see here. And of course, aligning it with the original problem statement, the original needs of the customers. And as we have this data-centric AI perspective that I kept pushing in this course, you will also understand why this started at the beginning with the data creation, with the data curation, and so on, right? So these two steps are really, really important here. Where does the data come from? How was it selected? And then finally, what do you do with the model? Because once you have it, again, this foundation model is trained on different data types, text, images, speech, or they can be, also structured data, 3D signals, anything else. But once you have this foundation model, this basis, this pre-training, you can then use it for a lot of different tasks in adapting it for the so-called downstream tasks. And at this stage, I think it's important to distinguish between two types of foundation models. On the one hand, we have discriminative AI. This would be everything that we did in the course so far. So traditional classification or regression tasks. And on the other hand, we have the generative AI, which is all about generating new content. We can discuss what is really new about this content in the exercise, but let's stick to that definition as of now. Now, in the past, I've worked more on the discriminative AI foundation models, right? So how can we build models where the downstream tasks are then these traditional cases of classification or regression? But today, we want to shift the focus a little bit because we kind of did that, not with foundation models on the left, but now we want to look into the generative AI part, right? And understand how does that work, because the majority of models, from my understanding, is in that area over here. So let's start and dive into that. One of the key things where foundation models also differ from the traditional approaches that we look at so far is the fact that it's built on different types of data, right? I showed that to you earlier. Text data, image data, structured data as well. So I think it's worth spending a few minutes on the challenges that arise when it comes to this multimodality in the data. And a really nice example that motivates why we do that, and that we can also take as a running example, is that this multimodality allows to describe images or videos or also audio, music with text, and then potentially also generate these type of media with text again. And if we take this image over here and paste it into a tool like ChatGPT, it can start describing the contents of this image on the left. So it will say something like, this is obviously a painting of realistic, high-resolution image of two people standing in a museum, observing a famous painting, and so on, right? So you can ask ChatGPT for a prompt that would generate such an image. And you can see that it gets two things. Two things are at the core here. The one hand, that it's about two people standing in a museum, and the second one, that it's about a potential Vincent van Gogh self-portrait with a bandaged ear. If we take this text now, that was already written like a prompt, we can also put it into a image generating tool like Dolly, for example, and it would generate an image like that. And you can see there's a difference between that. And let's dive deeper into why that's the case. So how does the model come up with its textual description, and why does the image recreated from this textual description look different in the end? And in order to do that, we need to understand how the knowledge is stored in a foundation model. So again, we have data with different origins, with different data types. And let's pick an example out of that. The two people standing in a museum, this text, these tokens. How is that represented in the model itself? In order to understand that, we need to look into the so-called embedding space that you can see right here. And an embedding space is a mathematical space where complex data like words, images are represented as so-called vectors or points over here, in a way that it captures their relationships or meaning, their semantic meaning in the real world. That means that similar items are close together, allowing the model to understand and process the relationships between them, right? So if we have, for example, king, queen, woman, and man, this means we could even do mathematical calculations with that, right? So if we would take king, for example, and subtract man, we could come up with queen. Or we could see that the difference, hopefully, if our model works right, between king and queen is the same difference between woman and man, because that's the only difference, the gender in this case, that separates these two words from a semantic perspective. And if we assume that this embedding space works correctly, this also means hopefully that our initial data that we have on the left there is represented accurately in this embedding space. So that's how it works for text and how it has been done for a long time. Now, how is visual data embedded? How are these semantic relationships embedded? And first of all, you could think it looks something like that, right? We had the precise words earlier, and now is the equivalent of that actually a full image? So, for example, the relationship between museum and art to soccer or football or soccer to a stadium. That is not really the case, because one thing that we utilize here, which we briefly touched upon when it came to the different algorithms, is for visual data the so-called convolution. That is the process where we apply a small filter, typically a matrix like the one that you can see over here, across an entire image. And it will detect specific patterns in there like edges or textures, and hopefully concentrate on the most important aspects of that, the most important features. So it slides over the data, combining values to create a simpler representation, a feature-focused representation. And this one is easier for the model to analyze, and that's the one that we can also find then in the embedding space. But you can see already that this is tough for these foundation models, because we have text data on the one hand, which works in a certain way, and now we have images or convoluted images, which also need their representation in the embedding space. And obviously it doesn't stop there, right? We have different types of data as well as audio data, for example, that also need their place in the embedding space. And of course, this audio data also needs to be somehow pre-processed in order to be represented accurately. So you could use, for example, a spectrogram, like you can see on the slide over here, which is a visual representation of the frequencies of the signal. So it transfers this unstructured audio file into, you could say, an image, something that could be looked at. And this hopefully represents the waveform then. So what you can take away from this is, obviously we have fundamentally different data types and representations in depicting our semantic relationship. And how does a foundation model deal with that challenge to have one embedding for everything here? And I think a great example to distinct that is to look at an analogy. I don't know if you've seen it, if you live in Germany or close by in Oberfranken or Franken in general, especially if you live in Würzburg. There's a great piece of art in the Würzburger Residenz, the Decken fresco. That was once commissioned by Bishop von Greifenklau, and it was painted by Giovanni Battista Tiepolo, an Italian artist and architect. And that is a great analogy to how foundation models attempt to build a comprehensive representation of the real world and the challenges they face, and also the shortcomings they potentially had. So the task for Giovanni was to draw the ceiling of the Würzburger Residenz with the task of draw the rising of the sun over the world, right? So Tiepolo worked on that. You can see an example over here. This is how the Residenz in Würzburg looks like. And then up here, you can see the fresco. So let's exemplify how foundation models attempt to build these world models using the available data, because Giovanni in his time also had only limited amounts of that data. So what are the challenges when it comes to that? First of all, you can see the image over here, and it depicts a representation of the world as the artist knew it. And the world in this case means Europe, Africa, America, and Asia. And obviously that was the worldview, right? So the data is considered complete if it's without missing information. Well, obviously a few things were missing here. And similarly, foundation models are limited by the data that we give to them and understanding that is able for them to comprehend in their training. So of course, any model can be rather complete or rather incomplete. But as you can see over here, the painter of the Deck fresco also had this limited view. It was not bad, don't get me wrong, but it was not complete. So completeness is a challenge when it comes to this multimodality. The second one is the context. So if you look at the depiction of Europe in the fresco, it centers on the bishop. That was, by the way, very typical for that time. So he was the one who commissioned the work. So obviously it was important to highlight his significance and influence. And this contextual emphasis mirrors how foundation models also rely on context to structure data, prioritize key elements in their representation to hopefully depict the relationships accurately, right? And so the context here refers to information and relevant details that surround and describe the data. But as you can see, obviously that is not the context in here makes sense if you know who commissioned that painting. But if the task was to draw the painting of the entire world, obviously this is at least debatable whether the bishop should be in the center over here. The next one is consistency. So you can see an ostrich over here, but Tiepo had never ever seen one himself in his life. So that was based solely on stories rather than first-hand observations. And again, the analogy to foundation models is it underscores the importance of of data consistency in the foundation models, because inaccurate or inconsistent data can lead to very flawed representations, right? Just like Tiepolo's rendering here of that bird is obviously inaccurate. So it is important to have that consistency. That was also one of our main challenges when we talked about data quality, if you recall that, right? So all copies or instances need to be the same across all data. And then fourth and finally, bias, right? So data bias occurs when the data used to train the model is not accurate or does not fully represent the target population, leading to somehow skewed or unfair outcomes. And in this fresco over here, you can see the depiction of Tiepolo himself and his son, by the way, as representatives of Europe. But of course, this is a fundamental bias, because it's a very limited and subjective view, neglecting the actual diversity of Europeans' population, right? And this illustrates how bias can shape representation, affecting not only the accuracy but also the fairness of these foundation models. So data completeness, context, consistency, and bias impact foundation models. And again, this all comes back to the data quality. Incomplete, inconsistent, or biased data can and will lead to flawed representations and then finally predictions. So that's something that we need to take into consideration when we are building these models. But let's come back to the example that we had earlier, right? From where we had the original image, generated text, and based on that text, we generated a new image. And let's look at a few of these challenges that we just mentioned being present in that very example over here. So if we look at the information that the model sees, you can read things like realistic high resolution image of two people standing, right? That's what we get depicted over here. We can also see that it is apparently on the right a Van Gogh painting characterized by vibrant colors and expressive brush strokes. So it kind of did capture those information of the image. But what it also did is it made assumption. So a part of this text is based on pure assumptions. And I don't want to say that we as humans don't make the same assumptions, but at least we cannot be certain from looking at the image of the left that all of these characteristics are part of that very image, right? We do not know that it's in a museum, but the text that we generate says it is. It says it's inspired by Van Gogh. Well, we don't know. And it says a lot about these two people, which are really out of focus in the image on the left. And it says a bunch of things about them, right? Like, two observers are diverse. One is a middle-aged black woman with shoulder-length hair wearing a smart casual outfit, and the other is a young South Asian man dressed in a trendy jacket and jeans. I'm not sure we can see all of that here, right? So this text is based on assumptions which highly correlate with the data space given by the left image, and we cannot be certain about them. And it becomes even absurd if we go one step further, because over here it even says that he's wearing jeans, which we cannot see on the left, which is again a assumption which will partly add new content to what we have what we already have in the image itself. And other aspects also, like the image that you can see, by the way, on the right is a starry night, which is something that has never been mentioned on the left, right? And are completely made up by the model. And my main point here is that all of this is happening because the data embedding, the representation in the semantic relationships are at least debatable, right? So it's an example how inconsistent data representation lead to no precise answers. Inspired by Van Gogh seems to be much more nearer to the Starry Night as a precise image in the data space compared to the portrait with bandaged ear, where we originally started from, right? So we can explain these flaws and these assumptions in the models if we look at the semantic relationship, which is in the real world very tough, right? I'm depicting it the way right now, like we could just do that. And in some cases you can in these semantic vector bases, especially when it comes to natural language. But that is, again, also a simplified depiction, right? So in a nutshell, the data embedding is a driver of a foundation model, of the ones that work well, but also of the ones that do not work so well. And this brings us to the question on how do they work in the first place, these generative foundation models that generate text or images. And for the remainder of the course, we will mostly concentrate on two types of data, one being text and the other ones being visual data types like images, videos, and so on. Now, especially the visual ones we'll cover mostly in the creative AI lecture, in the upcoming one. So in this remaining lecture right here, we will mostly concentrate on text now. However, that being said, of course, foundation models can be applied to all sorts of data types and not only on text, but we'll continue with text right now. And because we like historic examples today, I want to start with another one. This time it's not about the drawing on a ceiling, but a very interesting analogy on how these foundation models with text learn and how they see the world. So the allegory of the cave by Plato is an old metaphor that we can use for the challenges that foundation models face when it comes to an accurate depiction of our world through the data. So in this allegory, we have prisoners that you can see on the left over here. So these are the prisoners. And they are constrained to see only shadows that are being cast on the wall by this fire over here. And you can see those figures then produce those shadows. So what these prisoners do is they mistake the reality for these shadows because they have no direct experience of the actual objects themselves, right? They are prisoners. So all they can see is what's happening in that cave. And similarly, foundation models learn on vast amounts of data, but this data also only represents shadows or indirect or imperfect reflections of our real world. So these models can, of course, only approximate the reality based on that data that they are trained on, the shadows that the prisoners see on the wall here. Again, which may be and probably is limited, biased, and incomplete. And just as the prisoners must break free in this is allegory over here from the cave to really grasp the true reality, right? They have to break free and go out and see what the real world looks like. We also need to make sure that our foundation models somehow transcend their data constraints to better approximate the diversity and richness of the real world. But how do we do that? Well, let's first look at how these models work. So let's have a close look at the inner works of these language models. And to do that, let's start with a definition. So what is a language model in the first place? That's a very neat definition over here. Language models are computational models that have the capability to understand and generate human language. Language models have the transformative ability to predict the likelihood of a word sequence or generate new text based on a given input. And that's already an important information in here. So it seems to be about predicting, it seems to be about likelihoods. So probabilities seem to play a role and also a given input, right? I hope you get some supervised machine learning 101 vibes right now. Second, now what is a large language model? The large language models are advanced language models with massive parameter sizes. Remember the parameters, weights, and biases, and exceptional learning capabilities. The core model yields behind many large language models is the so-called self-attention module in transformer networks. We won't go into transformers and how they work. For now, let's just say it's a mechanism that is based on the theory of attention, meaning that these transformer-based neural networks hopefully capture important aspects and focus on them while ignoring unimportant aspects. And this is a fundamental building block for modern large language models. Okay, now what is a language model? Well, first of all, language models can be defined by their vocabulary. And we'll take the example that we had earlier with the university and the beautiful campus. So this is the vocabulary, this is the tokens that we have over here. Second, we have, of course, the sequence of tokens. So what is the length of a sentence over here? We have the language model itself, so that assigns probabilities to the sequence of tokens, and this probability tells us how good a sequence of tokens is. And then finally, of course, we do have this probability as the final characteristic. So from a mathematical standpoint, a language model appears pretty straightforward, yet it does have complexity to it. So it must possess implicit linguistic expertise. It needs to have semantic world knowledge to actually assign meaningful probabilities to these sequences. Now, if we say that we have these categories of the vocabulary, the sequence of tokens, language models, and the probability, let's dive into two examples that hopefully make this more clear what a language model is. So if we take, for instance, again, we have the same vocabulary up there, right? This stays constant. And now we have the sequence of tokens, beautiful campus, the university, right? Now, intuitively, we should assign this a very low probability due to its grammatical incorrectness, right? And this is, by the way, only based on syntactic knowledge in our depiction right now. So this sequence of tokens over here doesn't make sense from a syntactic standpoint. So it's grammatically incorrect. We don't really care about the meaning, but even only looking at that, we would assign this a low probability. On the other hand, it should assign a higher probability to a sentence like the campus has a beautiful university or the university has a beautiful campus. So we have now two different sequences of token that make sense from a syntactic standpoint, right? There are no grammatical errors in here. But if we look at this now from the perspective of semantics, right? Does this make sense? Do we see world knowledge in here? Then of course, we would assign one of these sequence of tokens a higher probability than the other, because we know with our world knowledge that despite both sentences having the same syntactic structure, only one of them really makes sense from a semantic perspective. And all of this, as you can see, comes down to the probabilistic foundations of large language models, and especially their autogressive behavior. So this means we have a series of tokens over here, and now we predict what would be the next word over here. And this is the idea of autoregression. And autoregression is a statistical modeling technique where the future values are predicted based on the combination of the past values over here of the variable itself. That's very typical in time series. Like if you look at stock markets, the earlier values have a high influence on the future values. Now, if we take a look at our exemplary sentence, the university has a beautiful, now the next possible word must be chosen from our vocabulary. So it can be anything over here from these ones. And the understanding of the history and of the context is now important as a foundation to define this sequence of conditional distributions. So you can frame it as, from the example over here, we can define the conditional probability distribution of choosing campus. So what is the conditional probability distribution of choosing campus given this sequence of tokens over here? And of course, we can formalize that probability distribution like you can see over here, yt for y smaller than t. And the conditional probability distribution, or CPD, is a statistical measure that describes the probability of an event occurring given that another event has already occurred. Again, this had nothing to do originally with large language models, but we utilize this conditional probability distribution right now to predict the next token, the chance that this next token in this case would be campus. And this means we can decompose this problem. So the problem of obtaining the probability for a sentence can be decomposed into single conditional probabilities, right? The chain of rule probabilities that you can see over here. Again, which is due to the fact that we have this autoregressive behavior of locally normalized large language models. And this is the basis on how the prediction of the next words work. So this both prompts and also answers the questions on how can language models generate content. So generally, a language model tries to find the next token, yt, which maximizes the conditional probability distribution given the history prior to that, so y smaller t. And that's how it can generate content. That's how it can give a guess about what the next token is. Again, but based only on probabilities. And this leaves us with this final formula for the conditional generation. And I have to make one thing really clear, I believe, right here. So it's not about a deterministic selection, but it is a probabilistic selection, which always does include randomness, right? So you could prompt the system 100 times and it will not always naturally return, in this case over here, campus. And to kind of control this randomness a little bit, you have this so-called temperature in language models over here. By the way, not only in language models, but also in other generative AI scenarios. And this temperature parameter T refers to the randomness. So it defines the willingness to explore, to allow for more randomness, or to allow for less randomness. To give you a few values over here, so if you set t equals 0, then it will deterministically always choose the most probable token yt at each position t, right? It will be entirely deterministic. You can look into the vector space, you will know precisely what will happen next. With t equals 1, you sample normally from the pure language model. And if you increase it above 1, right, up to infinitely, you sample from a uniform distribution of the entire vocabulary, which basically means any word can happen if we set it really, really high over there. And the interesting thing is that this temperature obviously drives not only randomness, but also the way that the generated text sound. It drives things that we would perceive as being creative. So that's very interesting. And there are tools that allow you to set this T. Of course, that's very mathematical, but if you work with Bing, for example, you can give it over here a few insights, like get creative inspiration. This will lead in the background to a way higher T, right? So what you do here explicitly is adjusting the T. Of course, it will decrease its accuracy, but you might come up with more creative ones. But we also see this in other cases, like Google Gemini, and ChatGPT also does that oftentimes, where they have small variations where different drafts are generated, right? So this temperature T obviously plays a large role. Now, one final thought though on the word of context that keeps reappearing here. So what is this in context learning all about? And to do that, we have to decide between different types of in context learning, right? It depends on the degree of information prior to the output. And the worst case in that regard is so-called zero-shot learning, right? So let's say you have no examples over here. You just give it the prompt cheese, and now the model predicts the answer given only a natural language description of the task, right? Translate English to German, cheese. That's a 0 shot. Now, in one shot, we do have one example, for example, the sea otter. And that means for the one shot in context learning, in addition to the task itself, like translate from English to German, we will also see a single example. And then the last one are few shots. So we give a few examples on what it could or what it should look like, right? And again, this is also due to tuning the model. Well, not tuning, that's not precisely correct, but prompting the model into a certain direction, right? And that's why also when you look into benchmarks of these large language models, you have cases for 0 shot, 1 shot, and also few shot cases. And the interesting thing is, coming back to our deployment lecture, of course you can use all of that in advanced large language models by calling up the API and giving it a message and then asking it to predict the next token. And that's how it's also done in reality when you have other services, think of our deployment logic, which call up the GPT logic in the background, right? And so I hope this gave you a rough, even if it was a rather superficial overview on how these large language models work, right? It's probabilistic nature, and you can set temperatures, right? Okay, now, next, let's have a look at 2 different examples. And let's look first at examples from research, because now we know a little bit more than we did 45 minutes ago. So let's have a look at what large language models can do. And let's have a societal perspective at first and ask, can large language models do harm? And look at the titles of these academic papers that you can see over here, right? Stereoset, measuring stereotypical bias in pre-trained language models. Attention is not all you need. The complicated case of ethically using large language models in healthcare and medicine, and large language models associate Muslims with violence. I think we understand better now why and how these models come up with their knowledge, right? Remember, they try to represent the real world, but things can go wrong along the way. Remember at this analogy of only looking at the shadows, right? Remember at the challenges that we have about completeness, consistency, context, and bias. And obviously, these all come into place here. So that's something that we can pick up for the discussion, but why does the large language model associate Muslims with violence? Because it's statistically more probable that Muslims commit violence, or because it has been said so in the data that was trained on, right? But it's not only societal. Obviously, it's also environmental. And again, we can't even go into that. We would need our distinct lecture, but extensive training of these models comes with huge challenges due to the energy demand. I mean, Google is literally building nuclear power plants, right? And just to give you an idea, so a single interaction of you with a large language model consumes as much power as leaving an LED light bulb on for 1 hour. So 1 hour of light in your room is the same as one of those prompts. So it's just extensive on what the environmental costs of that are. And it's something that we need to keep in mind. I want to say there are ideas and solutions on how to treat that. But as of now, I don't really think it's in the conscious of the users, and it should be, right? I know it's convenient, but if we ask the question, can large language models do harm? We saw they can do harm on a societal level. We can see that they can do harm on an environmental level. Now, where does the hype of ever large models come from? Larger models, more parameters, also consuming more more energy, as we just said. So existing empirical research shows that the ability to perform some tasks only emerge after a certain scale. So it becomes apparent that up to a certain threshold, language models do improve, but to make them really, really useful, you need a certain to pass a certain threshold. This builds a nice bridge to the beginning, in which we discovered that the parameter size of large language models heavily increased over years. So the models become better with increasing model size, to the best of our knowledge as of now. So let's come back to the beginning of this lecture, where we talked about the 2 steps of foundation models that you typically see in the real world. First, the pre-training on huge amounts of data, but now we haven't really talked about the fine-tuning yet. So that prompts a question on what happens in fine-tuning. So what happens once you have this pre-trained foundation model? Well, first of all, the fine-tuning typically does not create new capabilities. That means the capabilities were already part of that model somehow, but we modify the existing capabilities of that foundation model minimally. So what happens is that the model learns a so-called wrapper around its pre-existing capabilities, giving it the appearance of change. But in fact, there are no fundamental alterations to the foundation model itself. And these wrappers are often highly localized within the model's architecture, right? It will prune specific weights or neurons, or can revert the model back to some original pre-trained behavior, but nothing that is really, really deeply integrated. And these capabilities seemingly diminish or alter by fine-tuning. They can be rapidly reinstated with minimal additional training on relevant data. So that has been shown. So that suggests that fine-tuning does not erase the capabilities of my original foundation model, but it temporarily suppresses them, right? So the fine-tuning works with these wrappers and does not change or alters the underlying model capability that you had in the first place, but it just brings out specific capabilities or suppresses other ones. Let me give you an example. So this illustration over here aligns with this concept of pre-training a foundation model. Let's say we take a general task, such as autonomously driving a car in diverse winter and summer conditions. And now we want to fine-tune it for an adapted task, like it's not about winter and summer, but it's about driving a fast sports car. Now, the fine-tuning, so that was our original training first. Now what the fine-tuning does, it creates a wrapper around these existing capabilities and adjusts the model behavior for this new context, but without completely altering its foundational knowledge. But as you can see from this example over here, now a bunch of challenges arise, because if we go back to more nuanced areas of this foundation model or suppress others, the model could do unexpected things or create new scenarios. So since the fine-tuned wrapper may not fully integrate with the foundational knowledge, there's always a risk here that the model might react unpredictably. And that's an interesting case, because if you recall how the fine-tuning for many of the custom GPTs works, it's exactly that. And as you can see now, it comes with a bunch of challenges. Let's have a final view on what's happening in industry. And we started this entire lecture with a motivation on, does the power on AI concentrate too much with the big tech firms? And the debate around the AI concentration is illustrated through the case of stability AI and the leadership change that tied to concerns over the centralization, right? So sorry for the German over here, but we have these quotes from Emad Mostak, who criticized the concentration of AI power, advocating for more decentralization, right? Aligning with stability AI's ethics in promoting an open source generative AI that is decentralized, such as Stable Diffusion. But you can see how not only the technical capabilities, but also the money and the possible resources that you have come into play here. The other question is the financial, the business case behind that, right? So who pays the bill for the model training? Of course, you pay for the tokens when you use tools like GPT. And OpenAI, they have shown to have achieved a 2 billion revenue milestone. So they show that they can monetize AI services, for example, by offering API accesses with these token-based pricing that you can see over here. But we don't know a lot about the costs on the other side, right? But what we do know is, however they cover the cost, having this milestone of reaching 2 billion of revenue reflects that there is a successful strategy to monetizing these foundation models. Again, because of their scalability and because of their transferability. And this shows the complexities of the costs associated with innovation and also making a successful business model out of that, right? But as OpenAI says, no idea how we, or once said, no idea how we may one day generate revenue. Well, that's a quote of the past, obviously. Another thing that I would briefly like to mention, at least, is the Gemini controversy, centered around Google's decision to temporarily halt users from creating any images that would contain people with its Gemini model. And this move comprised concerns over ethical implications, as you can see over here, because the Gemini tool would generate pictures with potential harmful content, or would increase the diversity of pictures where there was no historic or factual relationship behind that. So it's interesting to see how also industry struggles with that. And then finally, let's have a look at what NVIDIA is up to and what they are doing. So one of the things that they are focusing right now is have these super photorealistic simulated environments, which can then be used for robotics or other AI applications with foundation models. I mean, let's see if we can shortly have a look at the video over here. Okay, I'll link it in the description. But they can use these complex simulated scenarios to build physical prototypes, do real-world testing environments, and so on. So that's a really interesting case. Now let me move further. And it's taken this step even further. So Eureka is an AI-driven framework which automates and optimizes the design of the reward functions using large language models. So it tries to have a human level of reward engineering to evaluate and improve the agents in these simulated environments, right? And you can see where all of this is going and what the potential applications of this means, especially in the production space when you talk about digital twins, when you talk about simulating anything first in a super realistic synthetic scenario. Okay, now let's come to a very quick summary. First of all, we see a very broad application of foundation models. So foundation models establish a very fundamental basis for a variety of AI applications with the pre-training, right? And then in downstream tasks, different things happen. It's all based on probabilities. So large language models are built upon probabilistic foundations, which you have to keep in mind. Right? It's only working on probabilities. And this brings up a larger discussion what is knowledge and are these models really smart? What is smartness and so on, which is something that we will discuss once we meet in person. The large language models can be easily integrated in existing applications functionalities, right? You saw the exemplary API call. It's really easy. Think back to our deployment lecture on this mesh up of microservices. The same applies here. And then really importantly, again, we call data-centric AI the data perspective, right? So again, this initiation phase, I know I keep repeating myself, but it's really important because the data that you choose will act as a representation of the real world. And the large language model will make decisions based on these shadows of the real world, which can have positive but also negative implications, as we discussed in this lecture. Okay, so as always, thank you very much for listening and see you soon. Bye bye.